Application development usually relies on a standard assumption about user directories. We treat them as passive data stores, a simple set of CRUD tables designed primarily to handle authentication and hold a few basic strings of text. The Project Nexus architecture utilizes a multi-layered stack of microservices, transforming the user node into a high-performance engine. The Nexus Members Directory is an API-first engine. It operates across 12 distinct dedicated microservices, coordinating everything from scheduling logic to user reporting. This engine actively processes real-time telemetry, executes multidimensional ranking algorithms to score user value, and resolves concurrent mutations within a live social graph. To understand how a system like this scales, we have to build the Nexus directory engine from first principles. We will deconstruct 3 specific engineering challenges required to make this work: executing geospatial routing, preventing database deadlocks, and normalizing human reputation into queryable math. Engineering the people layer as the foundational dependency for all higher-level modules is required for the platform to maintain stability at scale. This diagram maps out the primary database schema. The core user model is dense, utilizing over 80 individual columns for a single profile. To manage related complexity, specific domains like user skills, connections, and schedule availability orbit the core user table. To navigate this density, the database utilizes a full-text indexing strategy. Look at the paths scanning the unstructured fields. The engine creates composite indexes across first names, last names, bios, and legacy skill strings to allow rapid text queries. But unstructured text is difficult to compute against. Notice the dedicated user skills table. Here, skills are strictly categorized taxonomy, mapping string attributes to exact proficiency enums, from beginner to expert, and using Boolean flags to define if a user is offering or requesting the skill. When a client requests profile data, the API targets the v2 user/ID endpoint to fetch and compile all these disparate fields and relational mappings. This introduces an immediate architectural hazard. If you send the full data payload to the front end and rely on the client application to redact private information, you create an insecure system prone to data leaks. The Nexus backend solves this by injecting a 3-level profile visibility flag, public, members, or connections, directly into the database query execution plan. The API evaluates these flags before the query runs. Based purely on that logic, it dynamically alters the response. The endpoint will yield the full payload, return a 403 forbidden error, or output a heavily redacted object where personally identifiable fields are scrubbed. By isolating privacy logic deep at the query layer, the system guarantees data safety across all 12 dependent microservices before a single byte reaches the network. Moving from static individual profiles to an interactive social graph creates severe mechanical friction at the database level. Consider the API action required to connect 2 people. If user A and user B send a /v2/connections post request to each other at the exact same millisecond, the system risks instability. A naive database approach wraps each request in a transaction. When executed concurrently, these overlapping transactions create a race condition. This sequence diagram illustrates the resulting database deadlock. User A's transaction initiates and locks their specific row. User B's transaction initiates and locks their row. Here is the exact mechanical failure. User A's transaction needs to update user B's row, which is locked. User B's transaction needs to update user A's row, which is also locked. Both transactions wait infinitely for the inverse row to unlock. To prevent this, Nexus handles the concurrency logic inside the database transaction using a dedicated connection service. Watch the diagram reorganize. The system implements ordered row locks. Before any write occurs, the database deterministically sorts the required locks based strictly on the numerical hierarchy of the user IDs. Because the locks are acquired in the exact same sequence, regardless of who sent the request, the infinite wait is completely circumvented. The system safely forces a resolution, resulting in a single pending or accepted connection state. Social graph stability at scale relies on deterministic concurrency management. Simply throwing more compute power at the database will not solve a structural deadlock. The next systemic requirement is tracking dynamic presence states in real time, specifically whether a user is online, away, or set to do not disturb. Executing standard database writes for every single user click or mouse movement creates a massive I/O bottleneck that destroys disk performance. This split-screen architecture map shows the solution. Nexus implements a hybrid architecture that routes high-frequency traffic through the API gateway directly into a Redis cache, bypassing the disk entirely. The primary data route works like this. The client sends a heartbeat payload. The API writes that payload strictly to Redis, attaching it to a unique key containing the tenant ID and user ID. Every Redis key is assigned a strictly enforced 300-second time to live. You can see the timer resetting back to 300 seconds every time a new heartbeat hits the cache. However, historical presence data, like the exact timestamp of a user's last login, must still persist to the main database without triggering the I/O bottleneck we just avoided. To achieve this, the system implements a decoupling mechanism using a secondary presence throttle key. Look at the gate between the cache and the database. This throttle enforces a strict 60-second interval per user for actual disk writes. It allows one update through and drops all redundant persistence requests occurring within that window. If a user closes their browser and their heartbeat drops completely, a background cron worker sweeps the system to locate and clean up any stale keys. Achieving real-time state at scale requires treating the relational database purely as a historical ledger. The cache operates as the active state machine. Once server state and concurrency are stabilized, the architecture must solve for routing. It needs to surface the most valuable nodes in the network. Trust is typically treated as a qualitative, opaque concept. The challenge is operationalizing that human behavior into deterministic math. The engine uses two algorithms to do this. The first is the Nexus Score. This is a static 1,000-point composite that analyzes 6 distinct dimensions of user behavior to map members into 9 specific tiers. The second is CommunityRank, a dynamic algorithm used to continuously reevaluate a user's relative position among their peers. This formula overlay illustrates the CommunityRank calculation. The final score is a weighted combination of 3 variables: activity, contribution, and reputation. Notice how the data flows. Raw database metrics, like transaction counts and active listings, are aggregated over a 30-day look-back period. These raw numbers are then normalized on a 0 to 1 scale relative to the absolute maximums currently existing in the network, outputting the final score. Identity verification introduces a hard 1.1x multiplier to the final algorithmic rank for users holding the peer-endorsed badge. Nexus treats trust as a queryable database state, using these scores to dictate platform routing and search visibility. This map displays the complete operational architecture. Bringing these subsystems together reveals the density of a modern directory engine. Watch what happens when a client makes a GET request for their profile. The request enters the gateway and fragments across the ecosystem. The engine triggers massive concurrent orchestration. It executes geospatial Haversine proximity calculations to instantly locate nearby active users, validates current present states against the Redis cache, and resolves bidirectional database locks to map your connections. In that exact same millisecond, the request is computing the normalized CommunityRank and applying your privacy flags to the output payload. Ultimately, the people layer functions as the high-availability routing engine upon which all other business logic securely executes.